and welcome to the fourth webinar in the TMSI Expert Talk webinar series. My name is Rob Hartman and I will be your host for today. A special welcome, of course, to our speaker of today, Professor Sofiane Boudaoud from the University of Compiègne. Before we start with this presentation, I would like to mention some house rules so we can keep this webinar clear for everyone. As an attendee, all your microphones are muted, but if you want to ask a question to Professor Boudaoud or to TMSI, you can ask that through the Q&A button, which you can find in the bottom center of your screen. After Professor Boudaoud's presentation, I will go through the questions one by one so that Professor Boudaoud can answer them. We are now with about 30 attendees, so I hope you all enjoy the presentation. Professor Boudaoud, the floor is yours.
Thank you, Rob. Are you listening to me? Is it okay?
Yes, we can hear you. Okay,
so thank you. I'm grateful from this opportunity to participate to this very nice webinar and to promote high-density surface EMG technology. Thank you for all the guests, and I hope that you will enjoy this presentation. So rapidly, as said by Rob, my background is in electrical engineering, biomedical engineering, and especially in signal processing also related to electrophysiological data, and especially, of course, high-density surface EMG. So why we are interested in studying the neuromusculoskeletal system? So in my childhood, I practiced a lot sports, and especially basketball. I think that among people that are hearing this presentation, there are also many people that loved sport and perhaps also basketball. And my idol was Michael Jordan. And you have seen recently a nice series in Netflix that present Last Dance, the last season of Chicago Bulls. And I wondered and I was surprised how this guy that measure 1 meter 96 8 and 96 kilos weight is able to jump and to do these amazing motions. So this pushed my curiosity to go further and to try to understand how this magnificent machine, the neuromuscular system, is able to move and to do this kind of nice and amazing motions. So how it works, how it is driven, because of course there is an orchestra chief in the brain that do the perfect coordination of all the muscles to do this unbelievable motion. So how it can be assessed, efficiency in an non-invasive manner. So for example, for Michael Jordan, is it possible to understand what are the mechanisms of the locomotion, how Michael Jordan is able to do this motion, and how me, even with 20 years of training, I will not be able to reach this level. In the other side, we can ask also ourselves, in case of impairment, what happens to old people, for example? We know that aging is changing dramatically muscle configuration, brain configuration, cognition, locomotor properties. So is it possible also to assess aging, for example, or disease related to the neuromuscular system in a non-invasive way? This is the main question. So everything begins with the neuromuscular system that is composed by, the central nervous system that is linked to the peripheral nervous system through the spinal cord. And you have the longer neurons in the body, the motor neurons, that you can consider as electrical wire that are linking the spinal cord to fibers, muscle fibers. So a fiber is an element that is contractive. So if you inject currents to the fiber, you can contract this fiber. And you have thousands and hundreds of thousands of fiber within the muscle. So these fibers are regrouped in entities, functional entities, called motor units, and each motor unit is linked to one electrical wire to the spinal cord. So imagine that in your muscles, you have hundreds of wires that are piloting hundreds of motor units. So if you can compare it with, for example, artificial limb now, it's ridiculous how the actual technology is very far to the complexity of the natural organ. So you have hundreds of motors that can contract independently or in pool to generate the muscle contraction. So what happens? You have the electrical current that is spreading through the muscle tissues, and you have a mechanical response that is generated at the end of the muscles related to the tendons. And in the myotendinous complex, you have the generation of contraction, and the muscle force is applied on this tendon, on the musculoskeletal system, and generate finally the motion. And here, the amazing motion of Michael Jordan. He won the slam dunk contest of '97 with this incredible jump at 4 meters from the basket. So considering this complexity, how can we deal with the research now? So basically, with my modest experience now in this field, I have divided my research in 3 categories or in 3 axes. So in this presentation, we will focus on the first one. So of course, analysis and modeling also of surface EMG signals, because the modeling part is very important. We need models to understand better what happens in the physiology, because you can't access to all the experiments, to all the possibilities in a non-invasive manner. So this is very highly interdisciplinary: signal processing, physiology, biomechanics, computer science. Okay, everything is beginning from the neural drive, as you can see here. The music partition, I like using this word because you are dealing with a music partition, and this partition is played by each muscles, and the muscles, the music of the muscles is the motion. So imagine that your brain is an orchestra chief that is dealing with an orchestra with many musicians. Each musician is the muscle. You have almost 600 muscles in your body. So this neural drive, very complex recruitment pattern of the motor units, activate selectively each motor unit, as you can see in this picture, with impulsion. So you have firing of each motor unit at a specific time, and the specific motor units here is recruited. You can generate an electrical manifestation that can be measured at the surface using electrodes. And few milliseconds after the electromechanical delays, you have the generation of the force mechanical manifestation. And you can see here, for example, isometric contraction at different level of contraction. So the problem here is that this neural drive is non-observable in a non-invasive way. Another problem is that also the intrinsic force generated by one muscle is not accessible also. The only thing you have is the electrical response using electrodes. So experimental validation is hardly difficult. And this is the challenge also. How can we build new mechanism, new methodology for validation of what we understood here in surface EMG, and demonstrate that is related to the neural drive or related to the generation of the force? So my first axis is the complex inverse problem. Is it possible from the observation of these complex, non-stationary, evolutive, dynamic signals that resembles to a noise, to go back to what happens here, or some information to the activation pattern of the muscle? This is the first axe of research. Second one is that since going from surface EMG to the neural drive is very complex, is it possible to do the direct direction and to provide realistic, computer efficient neuromuscular model that can simulate for a specific recruitment pattern the surface EMG, the force, and also a relationship model between both surface EMG and force? So this is also very interesting. You can validate some methods developed in the axis 1. You can also test some physiological hypothesis and see what happens at the surface EMG and force. The third axis is that since you don't have many modalities to do the validation, is it possible to relate all the system to motion using some musculoskeletal model? So linking motion with motion capture, go back to some information to the generated force, relating the force with surface EMG and the surface EMG with the neural drive, and trying to validate this very complex chain by the only modalities, surface EMG and motion. So this is my third axis of research. Let's focus now on the axis 1. So as you know, many of you, the surface EMG is the results of the convolution of firing rates and electrical response of each motor units according to the size, the speed, the type of the fiber. You can see here the typology of the fiber. In the same time, the same recruitment pattern is used and convolved with the mechanical response of each motor unit to generate the twitches and the mechanical responses of each motor unit. And by an additive behavior, you obtain the global surface EMG and the muscle force. So let's go now to the analysis and processing of surface EMG. So classically, amplitude values like root mean square values, average rectified values are intensively used in clinical application and experimental application. But the problem is with this kind of measure is that you don't have so discriminative power. I mean that you could have many combination of recruitment of motor units that provide you the same value of the RMS or the ARV value. So this is not meaningful if you want to do something that is more precise, more sensitive to what happens inside your muscle. Knowing that in your muscle, you can see you have the effects of the position of the motor units, the size of the motor units, the depth of the motor units, the electrode used, so many parameters that can affect the surface EMG you obtain. So look here, for example, you have a slow motor unit that is a big motor unit, but it is at a deeper position than a fast motor unit or an intermediate motor unit that is smaller, okay, here. But since it is more at the surface, the contribution of this motor units will be bigger than the precedent. So don't consider the real size. Look to this one, the motor unit 6, fast fatigable. It's huge and big, but if you can see the contribution at the surface, it's very small. So how can we imagine that this is a very big motor unit, but just observing this, this shape of the motor unit action potential? So we have to imagine new descriptors, new methods that can be sensitive in a certain way to these differences. So after a deep screening of the surface EMG signals, we observed that the surface EMG signal is not really Gaussian. Gaussianity is just convenient for estimation and putting very large hypotheses. But in reality, it is not. So you can observe here, for example, some asymmetry, some pickedness of the motor of the probability density function. So is it interesting to challenge this and to go further in the shape of the probability density function, knowing that surface EMG can be considered of the sum of weighted random variable. Each motor units generate a random variable related to the position, the firing rate, the type, and many other parameters, and weighted by this parameter. So here you have the surface EMG, a random variable that is a weighted sum of other random variables. So what you measure depends also on the instrumentation. If you are using monopolar, you have a deeper, you have a huge volume of detection. But if you use other instrumentation or other electrode arrangement, this will change also the result you obtain. So be careful about using the electrode arrangement. So the shape of the probability density function seems to contain some information about the motor unit recruitment chain and the muscle activation bubble. So basically what we can provide is the very known high order statistics like skewness and kurtosis. These are indirect analysis. They are applied on the data, and they can give you information about the symmetry and the pigginess of the probability density function. More recently, I have developed a formalism core-shaped modeling that try to analyze directly the shape of the probability density function. So consider the probability density function as functions, not samples of data. You have really these functions. You try to smooth this function. You use this function. You work on the distribution domain, inverse distribution domain, and we can create some distances, some center of classes if we want to do clustering. And it's possible to do a realignment process and to extract some new metrics in this Euclidean space to measure the difference in shape between two shapes here. The advantage of this kind of method is that it's very robust and it is very sensitive to very small change in the probability density function. So for this purpose, I proposed after some robust shape distances that are specialized in some area of the probability density. For example, left shape distance for this tail, right shape distance for this tail, and central shape distance for the pickedness of the probability density function. So now let's talk about the instrumentation. Instrumentation is very important. So even if you are very clever and very you have facilities in signal processing, if your data are not relevant, it doesn't matter to continue the adventure. So I want, before talking now, that I never been paid by TMSI. This is my own opinion, and I want to share it with you. So honestly, from now 5-6 years, I'm working with the TMSI. The devices are amazing and great. The quality of the data is perfect, really. So you have a signal to noise ratio that is very high. You have, I never been faced to some saturation problem or artifacts. So in the majority of the cases, the data are very nice. And this is very important. If you want to estimate the probability density function of some random process, if you have noise, artifacts, problem of recording, a bad signal to noise ratio, it's impossible to do this very fine analysis. So you need the better signal you can have. And this kind of devices can provide us this kind of very high quality signals. So you can see here the grids I used for the experimentation. I will show after in few slides. And this is a very flexible grid that you can put over the muscles. There are many sizes. You have a small size and a big size, and you can manage the curvature of the muscles. And it's very comfortable to use this grid, and very easy to put them on the muscles. And this grid lets you to have access of a kind of map. So for the people that are familiar to EEG signal processing, it's exactly the same thing now. You can manage multi-channel analysis now here by considering a map of activation rather than one electrode. And I will show you that this is more robust than using just one EMG electrodes that you put. You don't know where you put this EMG electrode in your muscle. There is a strong variability, and you can conjecture or hypothesize two hypotheses that can be contrary. So you can decide that the muscle is in this situation or in another situation. It's the same muscle, but the position are different. So be careful on the placement of your electrodes. And if you are able to use a grid, because you will have an image. It's more robust to moving the grid over the muscle. So let's see these first applications. So what we want to do here is to study what happens when we are doing an anisometric contraction. So we are varying, not an anisometric, an anisotonic. So the contraction in the isometric with 90 degrees here for the biceps. We put the grids on the biceps brachii and we increase linearly the force from 0% MVC, maximum voluntary contraction, to 50% MVC. What we want to see here is to test the changing of the PDF shape according to the level of contraction. Remember, we want to develop new descriptor that seems to be sensitive to recruitment, activation of muscles. So what happens to the skewness or to the kurtosis if I increase the level of contraction? So we begin with the SNR matrix here. We do a channel selection. So here we have the SNR matrix, channel selection. We choose by thresholding which channel are over threshold on signal-to-noise ratio. We use also a Laplacian arrangement. Why? Because Laplacian arrangement is sensitive to what happens at the surface. So it depends what you want to do. If you want to see deeper in the muscle, use monopolar. If you want to see what happened at the surface, use the Laplacian. So for this example, we want to know what happens at the surface of the muscle related to the typology of the biceps brachii. As you know, you have fiber 1, fiber 2. The fiber 2 are at the surface, the fiber 1 are deeper in the biceps brachii. So after we have done PCA on this Laplacian arrangement, and what I am showing to you is the principal mode. For each subject, there is six subjects. And you can see the trends of the skewness and the kurtosis. What is interesting to see here is that we didn't standardize the position of the grid. We put the grid perhaps in different manner from one subject to the other. Despite this variability of positioning of the grids, you can see that we have in the skewness parameters a clear increase of the non-Gaussianity according to the level of contraction. So it happens something here. The signal is not Gaussian. It is Gaussian in the beginning because there is no contraction. But as you are recruiting more and more and more motor units, it seems that you are going, you are departing from Gaussianity. So this is an interesting thing. If you look to the kurtosis, it's not really clear because the kurtosis, as perhaps many of you know, the kurtosis is very sensitive to artifacts, to noise. So the kurtosis is not robust, but the skewness is more robust. We can see here that there is a trend, an increasing here non-Gaussianity according to the level of contraction from 0 to 50%. Another application that is very interesting is also denoising of surface EMG signals. Since now we have the access to a grid, is it possible to use this bidimensionality to enhance the denoising of signal of surface EMG signals? As many of you know, there is strong difficulty to denoise the surface EMG signal. Why? Because often the noise is superimposed with the spectral power density of the surface EMG. So this is a kind of joke with my students in engineering, in biomedical engineering. Often I ask them the question, if there is a 50 Hertz noise in your EMG, what you can do? And unfortunately, many of them answer, you use a notch filter. That you, as you know, you can't use a notch filter in surface EMG. Why? Because you will do a big hole in the spectral power density and you can't analyze your signal. So there is a problem in denoising surface EMG signals. You can perhaps reduce the white noise in some extent, reduce the artifact, but for example, for the 50 Hertz, it's difficult to extract the 50 Hertz. So let me present you a blind source separation technique at the second order that use canonical correlation analysis, okay, coupled to empirical mode decomposition. So we propose this method to denoise uterine surface EMG because in our team, we work on the muscle, the skeletal muscle, but also on the muscle of the myometron for preventing preterm and pre-birth, okay? So monitoring of the labor. So look here, what we deal, I don't want to go deeper in mathematics because you can go directly to the reference, to the paper to see the details, but what is the principle? The idea is to construct a matrix of data, another matrix of data that is delayed by some samples, compute the correlation between this matrix, do an eigenvalue decomposition, eigenvector eigenvalue decomposition, maximization of this eigenvalue decomposition, and a construction of a ranked component matrix here, and by an iterative process. And you can construct sources that are correlated, the most correlated at the front, the beginning, and the less correlated with themselves are ranked by the end. And this is very interesting because if you see to ICA, independent component analysis, there is no ranking of the sources. So it's very difficult to do a relationship between sources and physiology, noise, EMG, for example. In this approach, it's easy to know where is the noise and where is the EMG. So let's see, for example, here, you can do a classical threshold, classical thresholding on the canonical component, and let what is over the threshold is the EMG activity, and what is less the threshold is related to the noise, knowing that the noise is often non-correlated with himself. So what is correlated is the EMG, because the EMG is a kind of filtered noise. This is not the case for the white noise. The white noise is not filtered. So using this information of ranking related to the correlation, it's possible to do the separation. So we have proposed this two-step denoising, and after we improved this two-step by removing the EMD part and letting just the CCA part. And now what is interesting is that in the grid, the noise is not spreading in an homogeneous manner. In some electrodes, you will have a lot of noise. In some electrodes, less noise. So it's not meaningful to denoise everything and to put everything to the same level or the same signal to noise ratio. The idea here is to let the channels that are not noisy and to denoise the channels that are noisy, and to combine with a rule, letting the best channel and denoising the worst channel, and compute by the end a matrix that is the best combination of denoised channel. How we can do this? By ranking on the ratio between the noise you could have before the contraction and the noise plus signal you have during the contraction. Using this ratio, it's possible to do a multi-level thresholding on the canonical component. And look to this figure. You can see that we let the black sources and we eliminate the red sources. And among the red sources, we eliminate the 50 Hertz, knowing that the 50 Hertz is correlated with himself. So it's not possible to reduce the 50 Hertz using the same rules as the white noise. So thanks to this thresholding, it was possible to put away artifacts, 50 Hertz, and white noise in the same time. And look to the results. You can see here that the spectral power density is not affected by the denoising process. Look to the blue one with the huge 50 Hertz component here on the surface EMG. And look to the red one, that is the denoised one with this method. There is no noise and there is no distortion around the area of the peak of the 50 Hertz. And this is very interesting results. Let's move now to the last application, is how can we combine all this knowledge to better understand what happens at the muscle level. So using the denoising with CCA, using the shape distances I have exposed before, and using some kind of data fusion, because the question is, using the grid, I have to conserve the 64 channel, I have to select some of them, I have to do a threshold, which channel I have to maintain, to take the decision. So data fusion here is very important, because if you put away some channels, perhaps this channel contains some information that is interesting to your analysis. So channel selection is an open issue in high density surface EMG. How can I let some channels and put away the others? So what we have done here, we use image processing and image segmentation using watershed algorithm. That is an image processing approach often used in image processing. So here you can see we measure Isometric contraction of the biceps, the same protocol as before. You can see here the grid, how it is positioned. A dynamometer to measure the force of the joint of the elbow, and the measure of the 64-channel high-density surface EMG. The first step is to select which area I have to conserve in the different level of contraction. We have 30% of MVC, 50% of MVC, 70% of MVC. So if I am doing an analysis to analyze the trend, I want to analyze the trend of the PDF modification, the shape modification according to the level of contraction, to see if there is a rule of, or if there is a sensitivity of this change, this trend, according to some configuration, physiological configuration of the muscle. So look here, 30% MVC, 50% MVC, 70% MVC. So after this image segmentation, the final filter is the one by the end. That is a kind of mask of the three and the common area on the three. So we select, using the computed RMS with mean square maps, which area is active in the three level of contraction. And we let this. This is a decision, perhaps it's wrong. You can improve it, you can propose other alternative, but we have to take a choice. We have to do a selection of the channel. So look here, these results are by simulation, because we have a huge also model that simulates both electrical and mechanical manifestation of the muscles. And this model is very useful because we can compare the trends obtained by experimentation with the trends obtained by simulation and try to understand what is the hidden configuration. So look here, we have simulated 3 biceps braking. One that is considered as fast. It means that the proportion of type 2 is bigger than the other configurations. So type 2, type 1, the faster is with the most number of type 2 motor units, fast motor units. We have another muscle that is intermediate, a kind of equilibrium between slow and fast. And the last one is a slow one with more slow motor units than in the intermediate and the fast one. And we want to see if this difference in the composition of the ratio of type 1 and type 2 will interfere in the trends of the shape distances of the probability density function. The answer is yes, definitively. So look here, for example, to the kurtosis and the skewness using monopolar, bipolar, and Laplacian arrangement. And you can see that the trends are dependent on the electrode arrangement. So look here, for example, to the kurtosis. What we can observe is that we don't have exactly the same trend, and we can discriminate between the 3 muscles, meaning that the configuration, typology of the muscle should or seems to influence, change the Gaussianity of the surface EMG. So look here what happens. We have a signal in the beginning at 30% that is less non-Gaussian. It's more Gaussian because you recruit just few motor units. As you increase the level of contraction, you increase the number of motor units, you increase the non-Gaussianity. But what happens after there's a trend, you go back. Why? Because many of you know the central theorem. The central theorem tells us that at the asymptotic limit, if you increase the number of random variable, you will converge to a Gaussian. So it seems that we observe this on these trends. We begin with something that is not Gaussian, it's Gaussian, non-Gaussian, and return to Gaussianity. But we don't know the speed of return, we don't know the speed of growing. This is interesting also to study. What is the departure from Gaussianity according to the constitution of the muscle or other parameters of the muscles, okay? So this is simulation results. Let's see now some experimental results with 3 subjects. As we guess, we have also differences according to the subject. In the kurtosis, the skewness, we can see here that we have some tendencies that are similar. Look to the kurtosis in simulation and look to the kurtosis in experimental results. There are some similarity. It means that we are not so far with our simulation in some extent, because it's very difficult to make to conclude. Why? Because as you know, the placement of the motor unit is not the same for every people. So there is no two guy or two lady that have the same motor units placed at the same position in the muscle. It's unique. So this unicity of placement of the motor units is a kind of noise. And this can explain how the tendencies are not exactly the same. So we have to provide some robust measure that can be able to counteract to this variability of the placement of the motor units inside the muscles. Okay, but it seems that we observe in both simulation and experimentation some similar results. If we can see now the shape distances, left shape distance, right shape distance, central shape distance, we have also some trends that are interesting. So it means that these new shape distances can be used as a complementary tools to skewness and kurtosis to analyze in a more deeper way the deformation of the probability defection of surface EMG. So what is the concern now for all this? If we want to conclude to this presentation, keep in your mind that the number of electrodes you will use is critical. The quality of the device you will use is critical. The placement of the grid over the muscle is critical. Okay? The denoising of the data is critical. The reduction of the dimensionality, how number channel you will use, how you select the channel is critical. And also the signal processing approach you will use to extract the information. All these elements are key elements if you want to apply this in clinical application and to help the clinicians in improving the diagnosis or improving the understanding of the very complex system that we discussed now from, I think, 40 minutes together, the neuromuscular skeletal system. So thank you for your hearing. And I'm ready now for some questions.
Thank you very much, Professor Boudaoud, for this interesting
talk.
Thank
you, Rob.
We have not received any questions yet, but they might come in now. But in the meantime, I do have a question. Because you have used our grids, of course, and they have a fixed configuration of 8x8, so 64 in total. And there are two different ones with both have their own inter-electrode distances.
Yes.
Is there any ideal inter-electrode distance? So should it be bigger or smaller? Is there an ideal number, so to speak?
Very nice question. I think it depends on the scale of what you are observing. It's a kind of scanner, you know? So if you want to pixelize very precisely a small area, I think it's better to reduce the size and to increase the number of electrodes, or if you have a fixed number of electrodes, to reduce because you are sampling. It's like the Nyquist, you have to respect the Nyquist theorem. You are sampling, it's a spatial sampling. So you have to respect the sampling. As your sampling frequency is higher, it's better for you to obtain the best images that are relevant to a small area. Now, if you want to assess some microscopic behavior, you can enlarge and use the second size of your devices, the grid that is bigger. But be careful. When you put the big size of the grid on the biceps, you have the crosstalk with the brachialis. So we have developed also using canonical correlation analysis, an algorithm that is able, using the big size of grid, to separate the activity of the brachialis from the activity of the biceps brachii. So be careful at the scale at which you are observing. If you reduce the size, you reduce also the impact of the crosstalk. So you are focused on a very small area. So for example, this grid can be used for facial muscles. If you want to analyze some, facial motion, you can use the small size. Or if you want to assess a very small portion of the biceps brachii or any muscle you want. But if you want to assess a global behavior, you increase the size, because it's not the same. The weight of each electrode will differ if you use a huge surface or just a small piece of the muscle. It's not the same.
Okay, clear. Thank you. In the meantime, we've got some questions, so that's good.
Yes.
First one from, and apologies if I don't pronounce your name correctly, from Subramanian Liar. What are the typical dimensions of these motor units? 12 millimeters to 1 millimeter? Question mark. And secondly, are deeper motor units always bigger?
It depends on the muscle. It's not related to the deep, it's related to the type. Fast motor units are the bigger one, and they are the surface. For the biceps brachii, if it is type 2, we can go back to the typology of the fibers. Look, the size of the fiber will increase with the type. So here you have slow fibers, slow motor units that are small but resistant, fatigue resistant. So if you see, for example, to the sportmen that practice marathon or biathlon from Kenya, from Ethiopia, they are very thin because the muscles are very small. They are thin because they contain a majority of slow fiber, but they are very resistant to fatigue. If you see now the quadriceps of Usain Bolt, you can see that it's a huge muscle. So it's dominated by hypertrophied, fast fatigable, this size. So it depends on the functionality. If you are training for powerness, so you will increase the size of the type 2. If you need to increase your resistance to fatigue, you will make your slow fiber more resistant. So it's the training, the practice of sport that decide, of course, combined with genetics, that decide what is the configuration, the final configuration of your muscle and the size of the motor units that are in the muscle. For the biceps brachii, the big motor units are at the surface and the small motor units are more deeper. And the size of the motor units depend on the number of fiber you have within. If you have 100 fiber, it could have, for example, 3, 4, 5 millimeters of diameter, but it's not a circle. Here, it just for convenience, I put circle, but in reality, they are spread in an area and they are interconnected. So you can have 2 motor units that are spreading together in the same area, but it's not so easy to define the size of the motor units. It's an area.
Okay, I think that was a clear answer. If there is an additional question, please put it in. But in the meantime, we've received more, so that's good. From Lindert Schaken, if you denoise with CCA only, if you denoise with CCA only the channels that have noise, what effect does that have on further processing on your HD-EMG data?
It will have a very nice effect, because look here to the denoising process. If I put away everything that is beside this threshold, look, this means that the ratio between the energy before the contraction and the energy during the contraction, the ratio is near 1. So it means that you have the same level of activity and the same level of noise. So it's better to put away these channels, these sources, because they are not contributing in EMG. If you look to these first sources, the ratio is over 10. So it means that the EMG activity is 10 more important than the noise. So if you want to do EMG analysis, surface EMG analysis after, it's preferable to maintain the EMG activity and to put away the noise. So of course, CCA here will help us to better be related to the genesis of the signal, because you will not be faced to the noise effects and instrumentation effects, for example.
Okay, thank you. Another question which I can also answer from Subramanian Lear. Are these wet or dry electrodes? Well, these grids can be used with disposable stickers and with electrode gel. Yeah, and then the stickers make sure that the electrode grid sticks to the skin, and the gel makes sure that you have good contact between the electrode and the skin to get noise-free measurements, or at least as noise-free as possible.
Yes. To complete to the comment of Rob, it's very easy to put the grid because you have a kind of B-face adhesive. I don't know if I can show you. I don't have here, perhaps, no. So you have a B-face, look here, for this grid, for example, you put away one face of the adhesive, you put it on the grid. After you put the gel, as you are putting the marmalade on the bread, is exactly the same thing. And thanks to the second B-face protection, when you put the second B-face protection, you put away the additional gel you have. So when you do this, you let just the nice quantity of gel over each electrode. And there is no risk of short circuit or something like this. Everything is well done using this technique.
Yeah, thank you for the additional comments. Yeah, that's correct. Next question from Stephen 2. Are there limitations of starting by extracting 56 bipolar channels rather than using 64 monopolar channels?
Good question. The problem of the bipolar, I will explain you now why I don't use the bipolar. I explain you why. I don't have here, perhaps I look here, for example. For example, yes. The problem of the bipolar is that since you are doing the differentiation between two channels, you create a kind of symmetric motor unit action potential. You know the waves, it should be like this, negative and positive wave. And the problem is that this wave is very symmetric. What does it mean? It means that if you do the addition of these symmetric waves, many, at the surface, you will obtain a probability density function that will be symmetric. So to increase the asymmetry of the probability density function at the surface, is better to use electrode arrangements that favors asymmetry. So I prefer to use monopolar or Laplacian because they create, as you can see here, the monopolar, it's highly asymmetric. So you have a very big negative wave and a small positive wave. And if you do the convolution with the firing of the motor units at the surface, we guess that you will retrieve a percentage of this asymmetry in the probability density function. So yes, if you want to do probability shape density analysis, it's better to avoid bipolar measurement, from my point of view.
Okay, thank you. Next question from Hans de Weert. What muscles do you think are most amenable to this type of analysis? So, is there any difference in the muscles to which you can use this this analysis?
I don't understood very well the question. Is it?
Well, is there? I think the question, the idea behind the question is, can you use your method on all different muscles in the human body, or is there a difference between the different types of muscles you have?
It depends. It depends. I agree totally to this question. It depends on many things. As you know, many muscles are pinnated, and the pinnation angle should be at the surface level in this plan, but could be also at this. So you have the fibers that go from the surface to a deeper piece of the muscle. And in this situation, the firing go through this small piece of muscle, and you will have a kind of blowing activity. For example, in the you have this kind of signals in the gastrocnemion. So you have a blowing phenomenon and very localized analysis here. So I don't know if you apply blind source separation on sources that are not common on all the electrodes, that it will work. So you have to ensure that the sources almost are present in all the electrodes. So for example, for the biceps brachii, since the fibers are parallel, if you put the grids over the biceps brachii, almost you are sure that what you observe on the sources is contributing with different weights at all the electrodes on the surface. If you put this grid over areas with localized blowing, the sources that are estimated are not common for all the electrodes. So this can be introduced some error and uncertainty. So be careful in applying this method to the, yes, to the configuration of the muscle you are using.
Okay, thank you. I think that answers the question. At least that's also how I understood the question. If that's not correct, please put in another question. The next question from Leo Hogendorn. Very nice presentation, Professor Boudaoud. Can you elaborate a bit more on the clinical implications of your findings?
Thank you. Nice question. So I applied, yes, actually I am dealing with aging. So this is my concern. Actually, I am trying to develop this approach, this technique to better understand what is the aging mechanism. So this is an application. I can show you another application because I prepared some back slides. This also is interesting and should be interesting some of you. Look to this application. So this was done in collaboration with a very nice lab in robotics in Paris, Université Pierre-Marie Curie. Unfortunately, we didn't continue the collaboration. We has done, due to a lack of funding, we collaborate just 1 year and we stop. And it's not nice because I was very interested in this application. So, but it's not a problem. Let me expose you the things. In these labs, they propose a stabilometric platform that is dynamic because they want to assess what are the strategy of the cerebral palsy patients against some perturbation on the table, on the platform, on the floor. So imagine a child, you know that cerebral palsy has several levels. So the idea here is to assess if it is possible to relate what happens at the surface EMG level with the level of cerebral palsy disease. So the child go over the platform. There is some perturbation, dynamic perturbation in its dynamic stabilometry. And we recorded from the tibialis anterior and also the lateral gastrocnemius lateralis, we recorded 2 grids to see the activation and co-activation strategy during the perturbation. And we guess that further analyzing these signals could help us to discriminate between strategies of activation, co-activation of these 2 muscles during the maintaining of the equilibrium for cerebral palsy child. So this is a kind of clinical application.
Okay, thank you for sharing this additional information. Next question from David Beckway. It is known that the muscle changes with increasing age, e.g. sarcopenia, dynapenia. Could you comment on age-related changes as measured by surface EMG? And do you think it is possible to observe changes over time with surface EMG?
To be honest, actually, it's my concern. I want to use all this knowledge to monitor what you have told before. Yes, dynapenia, sarcopenia. So there are some mechanisms that are explained in the literature, in physiology, you know, muscle atrophy, fat thickness, fat infiltration, changing in the motor unit recruitment chain. So there are many things. But what we want to do now, and we are testing in simulation for now, we have a PhD thesis that is dedicated to developing a new model that is personalized to the patient and that simulate the aging. This is what we want to do. So the idea is to simulate all the mechanism and to see what happens at the surface with EMG. But for now, it's just a project. So we don't know if we will reach some results, but the idea is to prospect more deeper what happens with aging. Yes.
Okay, thank you. Last question for now, and it's almost an hour now, so that's a nice timing, I think. From Stacy Woods. We are looking at comparing motor unit data between children and adults. Muscle size is different, therefore the detection volume is also different. Would this affect the signal obtained? And is there any way to account for this difference?
Very nice question. Yes, I agree totally with you. You will have a ponderation of the anatomical configuration on your signals. So yes, even if you have the same number of muscle, of fiber, the same motor unit, the same placement of the motor unit, just change the radius of the muscle and reduce it or increase it and do a kind of, like universe expansion, you will observe differences in your signal, knowing that the physiology is the same. It's just a scaling effect. But yes, you will be faced to this. So be careful in comparing different size of, so you have to think about something that is robust to this size effect. I don't have the solution, but I will give you the advice. Think about something that is weighted. Perhaps you can create a parameter that is weighted by the radius, for example, I don't know, imagine that you use the Hermes value. This Hermes value, you will divide it by the radius of the muscle. So perhaps you can create something that is almost independent. I don't see totally independent, but something that is perhaps robust to the size effect of the muscle. So try to think about these things. Create descriptors, normalize with some anatomical parameters to get something that seems to be independent, like the maximum voluntary contraction. You are always reducing, you are always doing the reference to the maximum of force. So imagine the same thinking by the size effect or the radius expansion of the muscle.
Thank you once again for your answer.
Thank you for these very nice questions.
Yeah, and all the attendants, thank you very much for your questions.
Thank
and
you, Rob.
of course for joining this fourth webinar. I hope you all enjoyed the talk of Professor Boudaoud. I at least know that I did.
Yes. In my turn, I want to warmly thank Rob, thank TMSI for giving me this opportunity to discuss with you. So thank you, Rob. Thank you, TMSI. And if you need some, I put my email on the front. So please be free to contact me if you want to discuss, share, ask me a question. There is no problem. I have put here my email. So contact me by this email, and all the references are available. I think, Rob, you put the references in the biography.
We will send a follow-up email after this webinar. So in the coming days, in which we will send more information and also the contact information of Professor Boudaoud and his list of published papers concerning this topic.
I can share also the presentation on demand. So send me an email if you need these slides to be, there is no problem.
Yeah, perfect, good to know. Yeah, we will also make the recording of this webinar available on our website.
Okay, if there is a recording, it's very nice.
We will also share the link with everyone.
Nice. So give me the link, please, because it should be interesting also to share it with my students. It could be a pedagogical material.
Of course, we will. So yeah, it leaves me nothing but to point out that we will have more webinars after this one. The next one will be, I think, at the end of
I will put the slides.
Yeah, it's at the end of your presentation, isn't it? On the 24th of June.
I will do the job.
If I'm not mistaken. 26th of June, sorry, again at 4 p.m. And after that, we will have, we plan to have a monthly webinar. And then the next one is about Parkinson's disease. We don't have the correct title yet, so I only put in the subject of the talk by Dr. Ying Wang from the Radboud University here in Nijmegen in the Netherlands. So keep an eye out for our newsletters. And the last thing I want to do is say once again, thank you very much to Professor Boudaoud for his nice talk. And thank you to all the attendees for all your questions and joining this fourth webinar.
Thank you very much.
Have a nice day and stay safe.
Have a nice day. Bye.